So we know what routing is. We need to find a path through a switched network. We know that to find a path, we need to define the metric because we want to use what's called least cost routing, where links are assigned costs, and we choose a path which has a cost which is minimal of all possible paths from source to destination. What we want to look at today is some very basic strategies for routing. Not the algorithms for selecting the best path, but the strategies we take for using those paths. Yesterday we finished with a case of, well, we'll see when we go through our example. So routing strategies. The first strategy is fixed routing. The approach is that we learn about the network, the topology, the costs of links. So we discover some information about the structure of the network. Then we use that information to calculate the least cost paths from every source to every possible destination. So if there are 10 nodes, or 10 stations in the network, then we try to find all the least cost paths from station 1 to the other stations, and station 2 to the other stations, and so on. So find the information about the network, calculate the least cost paths, and then we store those least cost paths in routing tables, and we'll describe routing tables in the next slide. And then with fixed routing, we use that routing information to determine where our packets go through the network. With fixed routing, the routes are fixed for the duration of the network. We'll see strategy 3 is adaptive routing, where the routes are adapted during the operation of the network. That's the main difference. We either create the routes when we build the network, and they stay the same for the duration of the network with fixed routing, or with adaptive routing, we create the routes and continually update them. We adapt the routing as the network operation changes. So with fixed routing, we have a single permanent route for each source and destination pair. By permanent, we mean that route will stay the same even if the conditions in the network change. And that's one of the disadvantages we'll see for this approach. The routes are determined using a least cost routing algorithm. And that is, choose a path which has the minimal total cost. And there are different algorithms that can do that for us. We can do it in our head if we know a simple network, but with large networks we need a software algorithm to find the least cost paths. Dijkstra, Bellman, Ford, and other least cost routing algorithms can be used. Importantly, in fixed routing, the route is fixed. That is, you go and start your own company, an internet service provider, and you build a network throughout Thailand. You have switches all across the country and links between them. When you design and build this network, you know the topology of the network. You're the builder, you're the person who put the nodes and the links between them. You know the characteristics of those links. So you know the information about the network when you design and build it, and before you turn the network on, you calculate the least cost paths. And you store the information about the least cost paths in the switches or in a special node. And when we deliver data across the network, we just use those calculated least cost paths. And those least cost paths are fixed. If my network runs for 1 year, every packet going from source A to destination B will always take the same path. We do not change the path during the network operation, with some exceptions. Exceptions, maybe there's a major change in the topology. I build my network throughout Thailand. There are 50 different switches, 50 different nodes in the network. In 6 months' time, I decide I need another 3 nodes in one town or one area. So maybe I would recalculate my least cost routes at that point in time and use them for the delivery of the data. The point is that we do not change the routes depending upon the amount of traffic in the network. That is, if I'm sending from A to B from some path, because I calculated that when I built the network, and then all of a sudden a lot of traffic is going along that path because many people are trying to send in that same direction, and we get congestion there. Then with fixed routing, we don't care. We keep sending across that congested path. That's not good, but it's very simple. It's not good because when the network conditions change, that is the load, the amount of traffic being sent, the delay changes, we will always use the same route when in fact there may be better routes available. We're using suboptimal routes when we use fixed routing. Fixed routing is good because it's very simple. You create the routes when you build the network and you leave them alone. The alternative is adaptive routing, which is strategy 3, and the difference is that we continuously update the routes during network operation and automatically update those routes. That is, we have protocols that do it for us. As a result, if we find congestion when we're using adaptive routing, the routes should change such that we route around that congestion. And that's what's generally used in the internet. So, what have we missed? With fixed routing, there's no difference between routing with datagrams and virtual circuits. Because the routes are fixed, that is, there's one route from A to B, and that route stays the same. All our packets, whether it's a datagram packet switching or virtual circuit packet switching, follow that same route. Here's our simple network that we've shown and illustrated yesterday. How many least cost paths are there in this network? I think we may have answered that yesterday, but quickly, how many least cost paths in this network? How many in the network? How many least cost paths? No, not 5. More? How many least cost paths? How many from anywhere to anywhere? Not. How many? No. Higher? No. 6 nodes. We need a path from N1 to N2. We need a path from, so there should be a least cost path from N1 to N2. We need a path from N1 to N3, N1 to N4, to N5, N1 to N6. Sorry. And also we need a path from N2 to N1, N2 to N3, N2 to N4, and so on. So there are 5 here. N1, if N1 is the source, there are 5 paths. And if N2 is the source, there are another 5 paths. And since we have 6 possible sources, there are a total of 30 paths. That is, we need a path, a least cost path, from each source, each potential source to each potential destination. So if this was our network that we build across the country with 6 nodes, we would need to calculate the 30 least cost paths. 6 nodes, 6 by 5 in this case. What are they? Okay, we'd need to list all 30 and we could go and calculate let's do this set first. N1 to N2, least cost path. N1 to N2. The path is N1, N2. The cost is 2. The path from N1 to N3, the least cost path, no. N1, N4, N5, N3. N1, N4, N5, N3 has a cost of 3. N1 to N4, N1 to N4. Remember this? The last thing we covered yesterday was that if the least cost path from N1 to N3 goes via N4 and N5, it must mean that the least cost path from N1 to N4 is direct N1 to N4. Why? Because if there was a path from N1 to N4 via some other node, Nx for example, if this was true, then to get, and let's say, let's not give a cost because this number is too low. If this was true and this had a cost less than N1 to N4 direct, if there was a path with a lower cost than this path, then this path would be part of the path from N1 to N3. But that's not true. The path from N1 to N3 goes via N1 to N4, which implies the lowest cost path from N1 to N4 is direct from N1 to N4. There cannot be a path from N1 to N4 that is less than the direct connection. That is, there cannot exist a path like this that has a lower cost than this path. That's an important principle because we use that when we store this information. So just from this, we immediately know the lowest cost path from N1 to N4 is direct. And from N1 to N5, same principle, N1 to N5, the lowest cost way to get from N1 to N5 is via N4. If there was a lower way or a lower cost approach, then that would be included in this path. What's the cost from N1 to N5? 2. If there was a path from N1 to N5 with a cost of 1, then that would mean there's a path from N1 to N3 with a cost of 2. But we know that there's not a path from N1 to N3 with a cost of 2. The least cost is 3. N1 to N6, we've done that I think yesterday. N1, N4, N5, N6. And the cost was 4, wasn't it? N1 to N4 is 1. And we would do that for the other 25 paths, from N2 to all the possible destinations, from N3 to the destinations. N1, and to save our effort, we would use software to calculate that for us. Dijkstra's algorithm or similar can calculate these paths for us reasonably efficiently. Now, what we need to do is store this information in each node. So when we want to deliver packets from N1 to N6, we simply look at this information and use the routing path to determine where to deliver the packet. That is, let's say node 1 has a database of the paths. Node 1 would store all those paths. Similar node, all other nodes would have a database. So node 4 would have all of its paths, or all the known paths. Let's say node 4 stores this path, as well as others. In fact, and we'll also have node 5. So we calculate the paths and store information about those paths in the individual nodes if we do it in a distributed approach. So we store here N1, N4, N5, N6. After calculating this path and also the other paths, we send that information to the other nodes and store it in the individual nodes in some database. So focusing just on these three nodes, N1, N4 and N5, they would store this information. To get from N1 to N6, the path is N1, N4, N5, N6. Now, node 1 has some data to send, a packet. Contains some data and a header. Inside that header is a source address and a destination. Node 1 wants to send some data to node 6. So it creates a packet inside the header, source node 1, destination node 6. Node 1 looks in its database to determine where to send the packet to. So it sees, okay, source node 1, destination node 6. Look in my database, node 1 has the packet, matches this value, node 1 to node 6. I am node 1. The next node in the path is node 4. Node 1 sends this packet to node 4. Node 4 receives the packet, looks at the header. Destination is node 6. I'm not the destination, so it looks in its database. Node 4 looks. If the source is node 1 and the destination is node 6, and I am node 4, the next node should be node 5. So node 4 sends the packet onto node 5, and node 5 does the same thing. Look in the database. I need to reach node 6. The least cost paths tell me to send to node 6. The next node is node 6. Node 5 delivers to node 6. Node 6 receives the packet, looks at the header, realizes I am the destination of this packet. Let's process the data, consume the data. We've reached the destination. So that's how we use the least cost paths. But instead of storing the entire path in a database, we only need to store the next node in the path. Node 1 only needs to know that the next node is node 4. And then it's up to node 4 to know to deliver to node 5. And node 5 to know to deliver to node 6. So in fact, in our database, at each node, we only store the next node in the path. The database is referred to as a routing table. It's a table of information table of information about the least cost routes. And in particular, we have a table which contains the destination node that we want to reach, such as in this case, node 6, and node 6. and the next node in the path to reach that node. So to reach node 6, we send to node 4. So that would be part of the routing table for node 1. We may optionally store the path cost. It's not needed, but in practice it's normally used or stored there. It's not needed in the basic form. And we do that for all possible destinations. So node 1 would have a routing table which has 5 rows: destination node 2, destination node 3, node 4, node 5, node 6. And so 5 rows. The first row, the first column contains these destinations. The second column contains the next nodes in the path to reach those destinations. So there's no need to store the entire path. We only need to store the next node in the path. Because of this principle, if the least cost route from node 1 to node 3 is to node 4, if we send to node 4, then node 4 needs to get to node 3, and the least cost route from node 4 to node 3 is via node 5. So we send to node 5. Node 5 needs to get to node 3. The least cost route is direct to node 3. So we only store the next node in the path, not the entire path. It makes the routing table smaller, easier to manage, and the distribution of routing information much easier. So instead of storing all of this information, the routing table at node 1 if we ignore the cost to keep things simple, destination, either node 2, 3, 4, 5, and 6. Next node, next node, no, no. A routing table, the routing table for node N1, N1 is the source and needs to reach the destination node 2. What is the next node in the least cost path from N1 to N2? N2. To reach N3, eat N4. To reach N5, N6, those values. The next node in the path, that's all we store in the routing table. These were the least cost paths from node 1 to every destination, 2, 3, 4, 5, 6. These are the paths. At node 1, we simply store a table which indicates the destination we want to reach, 2, 3, 4, 5, 6, and the next node in the path, 2, 4, 4, 4, 4. So when a packet arrives at node 1, it checks the destination of the packet. Okay, destination is node 6. Look in the table, destination node 6, send to node 4. We send to node 4. Node 4 will have its own routing table. And we'll do the same thing. Destination node 6, look up in the table. To reach node 6, we send to next node, whichever it is. Node 5, I think, in this case. So this is how the routing information is stored in nodes in the network. So this table, we'll see it later on another slide. I want to make some notes of the steps we've taken. What we need to do for fixed routing and also for adaptive routing, the first step for all this to work is we need to learn about the network status. In our example, to calculate our least cost paths, for us to calculate this, we actually needed to know this information. We needed to know that N1 was connected to N4 via a link with a cost of 1 and in the reverse direction a cost of 7, and all the other information. So this is the network status information. That is the other nodes in the network, the other links in the network, and the costs associated with those links. And those costs may come from different metrics: delay, throughput, financial cost, different factors, whatever we choose in our network. First step is to know this information. Next step, we calculate the least cost paths. Least cost paths, least cost routes. That's what we did here, although we've only done it for 5 paths. We'd have to do it for the remaining 25 paths in our example. So we calculate all the least cost paths. Third step, store that information in routing tables. So once we've calculated the paths, we store that in routing tables, only storing the next node in the path, making the table simpler than having to store the entire path. And once we have that, we use the routing tables to forward data through the network. When we have data to send, we look at the destination of that data, which is stored in the header, and just look up the routing table to determine who's the next node we send it to. And then the next node does that, and so on, until we reach the destination. The first 3 steps we can classify as routing, and the last step, forwarding. Routing is a set of strategies, protocols, and algorithms used to create the routing tables. How do we learn the network status information? In our case, we built the network, so we know it. But in an adaptive routing, we need to get an update of what are the network costs, the link costs, and so on. So we need some way to learn the network status information. So there are routing protocols that do that for us, automatically do it. Because as things change, we need to get updates of those changes. How did we calculate least cost routes? In our case, we could do it manually. In a real network, we'd use an algorithm to do that for us. Then we store that information in routing tables. Where are those routing tables? 2 approaches. Store the routing tables on the individual nodes. That's what we did in our example. Node 1 had a routing table. Node 2 will have a separate routing table, as will the other nodes. Another approach is to centralize that information, put all of that information in the routing tables in one central routing table, stored on a special node. That's routing, finding that information. Forwarding is the process of using those routing tables to send the data through the network. So once we have data to send, simply look up the routing table, determine the next node to send to. So in fact, the processes can be independent of each other. We can be continually updating the routing tables and at the same time delivering packets by using those routing tables. So what node, so where do we store this information? We could store the routing tables on individual nodes or in a special centralized node. For example, if it's a special server in the network that could store that information, and the nodes would have to access that information from that special server. So if I created manually a routing table for SIT's network, which has 5 or 6 routers, 5 or 6 switches, so different nodes, I could create them, I could program them into one central node, and the individual nodes could access that information to find out where to send the data to.
And access every time the data can come to the node, or only the update?
It depends whether we use fixed or adaptive routing. In fixed routing, we'd just distribute that information to the individual nodes. In adaptive routing, we'd need to continually update and continually access that information. Here's an example of a centralized routing table, also called a routing directory. Table, directory, the same meaning in this case. We'll come back to that one. Here's the example that we started on. Previously, I created the routing table for node 1. Here it is. We saw to get to node 2, 3, 4, 5, 6. The next nodes are 2, 4, 4, 4, 4. That is this information, 2, 4, 4, 4, 4. And we could also do that for the other nodes, and it's done for us for the other nodes here. The routing tables for each of the 6 nodes. This is the distributed approach where each node has its own routing table. We can combine all of that information into one centralized routing table, which is here. And it contains the same information, it's just structured differently. From node 1 to reach node 2, send to next node 2. From node 1 to reach node 3, send to next node 4. This column is the same as the routing table for node 1. This column is the same as the routing table for node 2, and so on. So it's just a combination of those individual routing tables. So that's fixed routing. With fixed routing, we do these steps once. Or ideally, we only do it once when we build the network. With adaptive routing, we continually do these steps. Say, put it in a loop. Learn the network status information, calculate least cost routes, store in routing tables, and maybe 1 minute later, go and learn more or updated network status information. If it's changed, recalculate the least cost routes and update the routing tables and do it again and keep doing it, such that the routing tables try to always reflect the optimal routes in the network. And that's it for fixed routing and almost covers adaptive routing. Any questions on how to create a routing table?
How to create, we have step plan. And you taught me to create individual, but this one that's combined together.
You could do, depending on the approach we're using, you could either do a centralized approach where we have one table for the entire network, or a distributed approach where we have a table on each node. Okay, yeah. This is what's commonly used in the internet, a distributed approach, the distributed approach.
I think the centralized we have some redundant.
A centralized approach is mainly useful if we only have a small network which is fixed. Yeah. A large network which is controlled by different entities, distributed approach is much better. In fact, in the internet, there are more details of how routing is performed This is the simple view. So in summary, in fixed routing, we make the decision for the routes at the start of the network operation. When I build the network, I find the least cost routes. And they should not change over the operation of the network unless there's a major change in the network topology. We can either use centralized or distributed approach for choosing those routes. The network information comes from all nodes. That is, information about all links is known to calculate the least cost routes. There's never an update of the network information. We do it once and that's enough. In practice, it's only useful for very small and stable networks, networks that don't change so much. When networks are large and they're changing a lot, then we need to update our routes so that we choose routes which are close to optimal. So we need to continually do these steps, and that's what adaptive routing is. That's the basic approach, or a basic approach for a basic strategy for routing, and that's what's used in the internet today. It uses routing tables and so on. Another approach, if you forget all of that, then we can look at another approach, an approach that doesn't use these steps. It doesn't use routing tables. It doesn't learn about the network status. Flooding is an alternative strategy. If we want to get data from source to destination, say one data packet we want to get from node 1 to node 6, in flooding, we send copies of that one data packet to every node in the network. Not brute, well, similar concept of brute force in that, okay, we send to everyone, and as a result, the destination is guaranteed to receive a copy. It's just that everyone else gets a copy as well. It's like if I wanted to deliver a message to one particular student, I just give a copy of that message to everyone who's near me, and then they will pass it on to the people near them, and they will pass it on to the people near them, and eventually the destination will get a copy of it. That's flooding. Very simple, but can be very inefficient. So what we do, a copy of the original packet, if we have one piece of data to send, a copy of that original packet is sent to all neighbour nodes. The neighbour nodes are the nodes which are directly attached to that source node. When a neighbour node receives a copy, it forwards a copy of that packet to all of its neighbours. And when they receive a copy, they send to all of their neighbours, and so on. We would need some way to stop.
And include the neighbor that just sent to and send back.
So there are some exceptions that we'll go through, and we'll see to make it a little bit more efficient. We'll go through the steps. The good things about flooding, it's simple. All possible routes are tried. If I send to all my neighbours and they send to their neighbours, eventually a copy of the packet will pass through all possible routes in the network to the destination. As a result, at least one packet will traverse the path with the least number of hops. That can be useful sometimes if we want to find the path with the least number of hops. If I know nothing about the network, but I want to know what is the path with the least number of hops from my node to some other node, I can flood a packet through the network, and one of those packets will take the least hop path. Things like setting up a virtual circuit can take advantage of this. If we want a virtual circuit to take the path with the least number of hops, we can flood our request message, record all the paths, and the destination will reply with the least hop path. Another advantage is that all nodes are visited. If I want to distribute information to all nodes in the network, just flood the network. Send a copy to all my neighbours, therefore all my neighbours have a copy of that information, and then they send to their neighbours. Eventually everyone will get a copy of the information. And in fact, that's used in some adaptive routing protocols. To learn status about, or information about the network status, flooding is sometimes used. The problem with flooding is very inefficient. To get one packet from source to destination, I need to send many copies of that packet. That's wasteful of my network resources. We can increase the efficiency by introducing some limits on how many copies we send. We'll see them shortly, using a hop limit or selective flooding. But if we use them, in some cases we may not reach the destination. That's a problem. Let's look how it works. These are some of the rules that we apply. Let's illustrate them.
Can we use hop limit?
We'll illustrate the hop limit shortly, but we'll start simpler without the hop limit. Ignore the numbers in these packets. So what this diagram shows is our network topology, our 6 nodes. It's the same as our previous example. We don't care about link costs. We don't need to know about link costs in flooding. Because we send across every link, we're not going to choose based upon the costs. In this case, node 1 has 1 packet to send to node 6, the destination. For now, ignore the hop limit of 3. Ignore the number inside these packets. We'll come back to that case. So node 1 sends a copy of that packet to all of its neighbours. Node 1 has 3 neighbours, 3 links, 1, 2, 3, sends a copy to each of them. So node 3 will receive a copy of that 1 packet, node 2 and node 4 will receive a copy. And when those 3 nodes receive a copy, they will make copies and send to their neighbours. With the exception, the first rule, do not send back to the node that just sent us a copy. So focus on node 4. Node 4 received a packet from node 1. Node 4 will send a copy of that packet to its neighbours, 2, 3, 5. It does not send back to node 1. Node 1 just sent us the packet. There's no need to send a copy back because we know that node 1 already has a copy.
How they can know? You put some...
I just receive a packet. I receive a packet.
That I can have list of nodes that just missing.
We need the packet needs the address of the node that sent it. We know which link the packet came on. Node 4 knows that this link is attached to node 1. There's a cable coming into it. I receive a packet on that cable, on that link. Do not send it back on that link. That's all.
But no history.
Not yet, no. No history. Just do not send it back on the link that you just received it on. As a result, 4 will send 3 copies. Again, ignore the numbers inside. That's not relevant yet. Similar. 2 received a copy from 1 and will send to its neighbours, 3 and 4. It will not send back to 1. It just received from 1. And same for 3. Of course, this is happening at the same time. 4 is going to send a copy to 2, and at the same time, if we have a full duplex link, 2 is going to send a copy to 4. But they don't know that yet. As a result, let's go back. Node 4 is going to receive a packet from 2 and a packet from 3. So in the next step, we're going to receive 2 packets. As a result, For the first packet we receive, we'll send to our neighbours, except who we just received it from. And for the second packet we receive, we'll send to our neighbours. So node 4 is going to receive 2 packets from 2 and 3. So it sends a copy of that packet from 2 to 1, 3 and 5, and a copy of the packet from 3 to 2, 1 and 5. So we see it sends 2 packets to 1, 1 packet to 2, 1 to 3 and 2 to 5. Because at this stage it doesn't distinguish between those packets. It's got no way to know that they are the same packet.
Why duplicate?
Because it doesn't know whether this data in these packets is the same or not. All that it knows, I'm going to receive a packet from node 2. It contains some data. I'm about to receive a packet from node 3. It contains some data. We don't know that it actually comes from the first same original packet. Even though the data may be the same, the data may be, please give Steve 1,000 baht. Even though the data is the same on both of those packets, we don't know whether it actually means give me 1,000 baht 2 times, or if in fact it's a duplicate of the original one. We'll see we need sequence numbers if we want to distinguish duplicates. We'll cover that shortly. In this very simple case, we receive 2 packets, the first one from node 2, so we send a copy to node 1, 3 and 5. We also receive a packet from node 3 and send a copy to 2, 1 and 5.
How about if hop limit is 4?
No hop limit yet. The same thing happens for the other nodes. 2 received a packet from 3 and 4. So it's going to send copies to 1, 3 and 4. 3 received some packets, it sends copies. 5 previously received a packet, in fact 2. It sends copies. First thing we notice, packets are arriving at the destination. In fact, when node 3 transmitted its first copy, node 6 will receive the packet. Node 6 is the destination. So we get the data from source to destination. In fact, we get multiple copies of the data from source to destination. Also, we notice data is being delivered to all possible nodes in the network. Everyone has received a copy after these steps. And the other thing we notice is that there are many copies of that one packet transmitted in the network. So we're delivering the data to the destination, good. Everyone's receiving a copy. That can be useful sometimes. The problem is that it's very inefficient. To deliver one packet from node 1 to node 6, we've had to transmit 3 plus another, what's this, 9, that's 12 transmissions, plus another, count all these, 30 plus transmissions to get one packet from node 1 to node 6. If we used fixed routing and our least cost routes, how many transmissions would we need to get one packet from node 1 to node 6? If we used our previous approach, how many? 3 transmissions. We would transmit on the path from node 1 to node 4, that's 1, 4 to 5, that's 2, and 5 to 6. To get data from node 1 to node 6 with fixed or adaptive routing, 3 transmissions needed. With flooding, we've used more than 30 transmissions. That's where we say it's very inefficient because we're wasting the network resources to deliver that data. How can we improve upon the efficiency? How can we reduce the number of transmissions? And we've seen some of them, or we've heard about some of them. One approach, introduce a hop limit. And that's what this number indicates in the box. In the first packet we send from the source, we include inside the header a value of how many hops we want this packet to traverse. Let's draw the packet. The packet has some data, and in the header we have a source address, node 1, a destination address, node 6, and now let's include a hop limit. And in this example, let's set it to 3. The initial value is set by the source. What 3 means is that we want copies of this packet to traverse up to a maximum of 3 hops, after which do not send any more copies. So how it works is that the packet contains in the header a hop limit, and that's the number here, 333. The same, when we copy that packet, it contains the same information. Node 1, node 6, hop limit of 3. We transmit to our neighbours. When a node receives, they decrement the hop limit. Node 4 receives, has hop limit of 3, reduces it to 2. If the hop limit is greater than 0, we can transmit to our neighbours. If the hop limit is 0, do not transmit. So they all reduce it to 2 and transmit. In the next phase, when they transmit again, it's reduced to 1. These 2 packets which are transmitted from 4 to node 1, when 1 receives them, it would decrease to 0 and not transmit, because we've reached the limit, we've reached 0. As a result, the packets never go more than 3 hops in the network. What if our original hop limit was 2? What's the difference? Less packets sent. If our original hop limit was 2, this value would not be 3, it would be 2. We'd send to our neighbours. When the neighbours receive it, they will decrease it to 1. So all the values here would be 1. And when the next nodes receive it, so node 4 is going to receive a packet from node 3 with hop limit of 1, not 2, and from node 2 with a hop limit of 1. When it receives them, it decreases it to 0 and does not send on because it's 0. So in fact, if the hop limit was 2, none of these packets would be transmitted. The total transmissions would be limited to 12, not 30 plus transmissions. So we reduce the number of transmissions by using a lower hop limit. What's the disadvantage? In this case, is there a disadvantage in this example? Compare the hop limit. Hop limit 3, hop limit 2. With a hop limit of 2, we transmit less packets. That's good.
But maybe not reach the destination.
Maybe not reach the destination. Did it in this case?
No.
Yes, it did.
In this case, 2 is okay.
With a hop limit of 2, source is 1, destination is 6, it does reach the destination.
Okay.
That's good. That's what we want. Hop limit of 1. Less packets transmitted, only 3 transmitted. Do we reach the destination? No. We'd transmit to 3, 2 and 4. They would not transmit on because it would be down to 0. Introducing a hop limit will reduce the number of transmissions, but may mean that we may not reach the destination. That's the trade-off there. Next thing we can introduce, a sequence number. When we create the original packet, sorry, in the header include another value, a sequence number. Every original piece of data has a unique sequence number. So the first piece of data that I want to send from node 1 to node 6, let's give it sequence number 1 or 0, whatever, just a unique value. When we copy that packet and send to our 3 neighbours, it has the same sequence number in each copy. So these 3 packets all look the same. Same header, same source, destination, hop limit and sequence number. To go back to our original example, hop limit was 3. So we transmit to our 3 neighbours. They make copies. All the copies still have the sequence number 1. Transmit to their neighbours, but we have some extra processing. When we receive a packet, if we focus on node 4, node 4 received a packet from node 1. It contains sequence number 1. When it receives a packet, it keeps track, or it keeps a history of the sequence numbers it's received and sent on. So after receiving the first copy, that is when we receive this packet at node 4 records in memory, I've received packet with sequence number 1 and transmits that to its neighbours. So node 4 transmits to its 3 neighbours. So now when the next step, node 4 is going to receive a copy from 2 and 3. These 2 packets have sequence number of 1 as well. All of the copies of that original packet have the same sequence number. When node 4 receives these 2 copies, it checks, I've already received a packet with sequence number 1. I've already sent it to my neighbours. If I receive more, just discard them. Do not retransmit to your neighbours. There's no point because we've already sent a copy of that packet to our neighbours. That is, when node 4 receives these 2, these 6 transmissions will not exist. It will not transmit to its neighbours. That reduces the number of transmissions. So by using sequence numbers, we can detect if we receive duplicate packets.
Have to compare 2 packets together, and if the receive,
Compare the sequence numbers of the 2 packets.
if the sequence number is the same, then only one.
If no, compare the sequence number of a received packet with the record of what we've already received. So we've got this extra information stored at a node. A list of packets that we've received and transmitted to our neighbours.
Can I say it receives only 1 copy of the sequence number each?
Receive.
One copy of
If we
each
receive.
packet with the same sequence.
If we receive, let's look at node 5 for example. Node 5 is about to receive 2 copies of a packet with the same sequence number. So what it will do, it will receive 2 copies, that's fine. It will transmit, it will make copies of the first one, transmit to its neighbours, and then it will have a record. Node 5 has received and transmitted packet with sequence number 1 to its neighbours. So for the second packet that it's received, it does not retransmit. You only want to send 1 copy of the packet to all your neighbours.
So if node 5 recognize packet from 4 first, then the packet from 3 will ignore.
Yes, effectively ignores.
Because packet from 4 and 3 have the same header.
Same sequence number.
Same header.
Yep.
Input or header the same one.
Yep. So, yes, so it's detecting duplicate packets. If we, by including the sequence number, we can check, okay, everything in the header is the same, everything in the data is the same, this is the same packet as what I've received previously.
And can sequence number change during sending?
For the original packet, the sequence number doesn't change. But now, sometime later, node 1 wants to send more data to node 6. The first piece of data was, please give Steve 1,000 baht, and then it sends more, please give Steve 2,000 baht. Different data. It increases the sequence number in the second packet. So sequence number 2 would be in the second packet.
If we have no sequence number, can we treat like this? We can compare all the packets. It's the same, send only one.
But if we don't have a sequence number, what happens? If there was no sequence number, everything in the packet looks the same. And then there's a second packet that arrives and everything looks the same. The data looks the same. The data is the same, identical data, identical header. Do we know if it's a copy of the original packet or it's in fact two unique packets with just the same data? Maybe node 1 has sent 2 messages to node 6, both of them saying, please give Steve 1,000 baht. Maybe node 1's intention is to send 2 messages to 6. So without a sequence number, there's no way to distinguish whether this is a copy of this or if it's in fact unique.
Okay.
With a sequence number, this one will have a sequence number of 1. If it's a copy, it will also have a sequence number of 1. If it's unique, it will have a different sequence number. That's where we need the sequence numbers.
It comes from only the source node, sequence number.
Yes, the source node sets the sequence number.
And in the network, you compare everyone. If you have duplicate, you send only one. If I have 3, send only one. 4, send only one.
Yes, the intention, just send one copy of the packet to your neighbours, because that's sufficient.
Okay. Sequence number.
So I think we've gone through all but one of these extensions. Only forward the packet once. Firstly, don't send back to the node that just sent the packet to you. That's the first rule. Only send the packet once. Detect duplicates using sequence numbers. That was this case we just went through. You may include a hop limit. If you don't want the packet to be sent forever, if we have some error in the network and there's a loop, it will keep being sent. So by introducing a hop limit, eventually nodes will stop transmitting. The problem with a hop limit is that it may be too small such that the destination doesn't receive a copy. That's a problem. One last approach, selective flooding. Flooding, send to all your neighbours, with some exceptions. Selective flooding, send to a selection, a subset of your neighbours. By sending to a subset of your neighbours, not all of them, you reduce the number of transmissions, but again, we may not get to the destination in the least hop path, and if we have a hop limit, we may not get there at all. Let's see some examples of selective flooding. Let's just focus on node 1, which has three neighbours. We don't care who they are. Let's say node 1 has a lot of data to send. So data 1, data 2, data 3, these are the packets and more. With full flooding, when we have a packet to send, we make a copy and send to all of our neighbours. With selective flooding, we select some of our neighbours to send to. And there are different approaches to selecting your neighbours. Random-based is one approach. with the random selective flooding, you've got 3 neighbours, randomly choose one of them. So my first packet, let's say this is neighbour 1, 2 and 3. One approach, randomly choose one of your neighbours to send a copy to. Send the first packet to neighbour 1. The next piece of data I have to transmit, again randomly choose which neighbour to send to. Maybe I choose node 3 the next time. Maybe the next time node 3. The next time node 2. Node 3, node 1. And randomly choose the neighbours. As a result, if we have a uniform random or select from a uniform distribution, then of my many packets, these original packets, maybe I have 1,000 packets, 33% on average will go to node 1, 33% will go to node 2, and 33% will go to node 3. If we're using a random selection and we have many possible random attempts, then a third should go to one node, a third to another neighbour, and a third to the other neighbour. So that's not very random. We'd have to draw more packets to show the full randomness here. That is, some are sent to node 1, some are sent to node 2, and some are sent to node 3, and just which one is chosen randomly. We don't have to choose one neighbour, we could randomly choose 2 of the 3 neighbours. That has benefit because we distribute the packet across more paths. If we choose just one neighbour randomly, what happens in our network? If we choose one neighbour randomly, and every node does that, our packet will take a random path through the network. Let's say node 1 chooses node 2, node 2 chooses node 4, 4 chooses node 1, 1 chooses node 3, node 4, node 5, node 3, node 6. We take a random path through the network, one path. We'll eventually get to the destination if we don't have a hop limit, but it just may take a long time. It's very unlikely to take the path with the least number of hops, so that's the disadvantage there. If we choose 2 random neighbours, then we take 2 random paths through the network. So there's a higher chance that we'll use a better path from source to destination. It's like you want to drive into Bangkok, just randomly choose intersections, and when you come to an intersection, choose which direction to go randomly. Okay, go left, okay, next one go right, go straight ahead. Eventually you'll get there, but it may take a long time. It may be driving for days and weeks. We can use random flooding. Especially, let's say, instead of having 3 links to choose from, I have 10 links to choose from. Randomly choose 8 of those 10 instead of the full 10. Round robin. Take in turns of the links. Round robin means you've got 3 to choose from. First packet goes to node 1, the second goes to node 2, the third goes to node 3, the fourth to 1, 2, 3, 1, 2, 3. Original packet 1, and then 2, then 3, 1, 2, 3, and so on. 1, 2, 3. Again, 33% of the packets will go to node 1, 33% to node 2, and 33% to node 3. It's just the way that we select those nodes. Probability based. In fact, random is probability based. We have an equal probability of using each link. Let's give some weighting to nodes or to neighbours. Let's say this link has a data rate of 10 megabits per second. This is 5 and this is 5. So one approach may be, okay, we've got 3 links to choose from. We're going to use them all, but this one's fastest. Let's use this one more often. So give some weighting that is 50% of the time we want to use this link, 25% of the time these other 2 links. Again, we can randomly select, or it could be round robin based. That is, first packet, second packet, third packet, fourth packet, 5, 6. That is 2 to this one, and then 1 to each of them. That is round robin based, or random. Randomly choose the neighbours to send to, but weight that such that 50% of the time we choose this node, 25% this node, and 25% this node. So that's a probability-based selection where we assign a probability based upon which one we want to use more often, maybe based on the characteristics of that link. So that's selective flooding. We reduce the number of transmissions because we don't send to all of our neighbours, but we reduce the number of paths we take in the network. We don't send packets across all possible paths. All right, I think we've covered this. By reducing the hop limit, we reduce the number of packets transmitted. You could count how many packets were transmitted. And we've covered 2 or 3 simple examples of selective flooding. And that's flooding covered. Completely different than our least cost routing. Not very useful in large networks, except for very special purposes. For example, I want to tell every node some information. I want to tell every node what my current status of my links are, such that they can update their network status information. I can create a packet, include the link status information, and flood it to all the nodes in the network. Everyone will receive a copy. It's very easy to do. I just send to my neighbours, they send to their neighbours. Eventually, everyone receives a copy of that information. So flooding can be used to distribute information to many nodes, or if we don't know anything about the topology of the network, and it's very costly to learn about the topology, then flooding can be used. But very inefficient. Last strategy, adaptive routing, and we've mentioned this. It's basically an extension of fixed routing. Because the network conditions change over time, the costs of the links may change. If the cost represents delay, the delay may be changing every second. It may be fluctuating. Therefore, when we calculate the least cost routes, we need updates of the costs of each link, that is, updates of the network status information. So adaptive routing, we have a protocol that tries to collect these updates. As a result, we can recalculate the least cost routes and update our routing tables. And I think that's all about these routing strategies. Adaptive routing is what's used in the internet and most packet switch networks today. It can deliver improved performance compared to fixed routing because we are more likely to use optimal paths. If we always know new information about the network status, it's more likely we'll choose the best path through the network, the least cost paths. If I use fixed routing, I choose the least cost path, but if something changes, I may no longer be using that least cost path, the least cost path. So adaptive routing can improve the performance. The disadvantages of adaptive routing is it's complex. We need more complex algorithms for recalculating the least cost paths. And we need some overhead of updating the information. Some overhead is incurred. And the basic trade-off is the more information we receive about the network status and the more often we receive that information, the more likely we can choose an optimal path. That is, the better path we choose. That's the good thing. We want to receive a lot of information and regularly so that we can always choose the best path. But the more information we receive and the more regular we receive that, the larger the overhead of collecting that information. So we'd like to minimize the overhead but maximize the chance that we can choose the best path. And that's where adaptive routing algorithms need to make some design choices to choose the right trade-off there. If we get updates very frequently, we may have problems in that the routes that we select keep changing. They oscillate, and that can impact on the performance of the data delivery. If we get updates too infrequently, too slowly, then it means that information that we receive may be irrelevant. I get an update once a year about the congestion in the road traffic in Bangkok. That's not very relevant for me, because between now and 1 year's time, all of that information may change. So we need updates on a frequent basis, but not too frequent, such that we incur too much overhead. Oscillation, the routes keep changing. That is, from source A to destination B, I choose route 1 to go from A to B. I send my packets, but then immediately something changes and I choose route 2, a different path. And I start sending my packets across that. And then I get an update and it changes, and okay, I realise I should use route 1 again, send my packets across there. And then I change back to route 2 and I keep changing. The problem with that is that some packets are taking route 1, others are taking route 2, and they may incur different delays. So packets are arriving at the destination out of order, especially if the paths are a different distance. And that can impact on applications, especially video and voice applications. The varying delay impacts upon applications.
Accuracy, but important in timeliness.
Timeliness, but also the receiver needs to put them back into order. That's an additional complexity. Yeah.
We have sequence number, then we can arrange it.
Even if we have sequence numbers, that's some extra processing that's needed at the receiver to do that.
Our order is not so important in we have sequence number.
Yeah, but it's still something extra we need to do. In order would be better.
Yeah. Order is okay.
So we'd like to avoid such frequent changes. So you know everything you need to know about routing so far. That is, if it's a long time between updates, then the information that we get and we make a decision based upon may not reflect the current status of the network. I make a decision thinking that this path is going to be better, but since that time I make the decision and started using that path, that has changed.
Maybe it's like out of date.
It's out of date. It's irrelevant at that stage. Yep. And that finishes for today, and we'll continue next week. We may briefly summarise on routing and move on to the next topic.